Hi, this is our first video on chapter 14, which is chemical equilibrium. This particular chapter is a very significant chapter. It is very, very important that you master all of the concepts, and skills in this particular chapter, because chemical equilibrium will be our life for the next 3 chapters. So chapter 14, chapter 15, chapter 16, and it will also pop up again in chapters 18 and 19. So equilibrium is huge. It's a huge concept, and that's why the first question on the AP exam in the free response section and the calculator section is always an equilibrium question. So hang on to your hats, really work hard on this, get this stuff down, and you'll be just fine for the next few chapters. So let's move on. Equilibrium is a state in which there are no observable changes as time goes by. Chemical equilibrium is achieved when the rates of the forward and reverse reactions are equal and the concentrations of the reactants and the products remain constant. The second one is actually a result of the first one, because as you know, a dynamic equilibrium of any type is when the rate of the forward process and the rate of the reverse process are equal, and that they're happening at the same time and at the same rate. So we can have physical equilibria, like liquid water in equilibrium with gaseous water. So the liquid water is being converted into gaseous water. It's vaporizing, but at the same time the gaseous water is condensing back to liquid water. It's the two opposing processes, and they're happening at the same time and at the same rate. So if that's true, then the amounts of each of those things should be the same. The concentration of each of those things should technically not change. And so that's how we get a dynamic equilibrium. That's how we get change through constancy, or constancy through change is what I should say. We get constancy through change, because we have a change occurring. Liquid is becoming gas and gas is becoming liquid. But we have constancy in the sense that the concentrations of each of those things should not change. To the left, you have a bulb in which you see a reddish brown gaseous, or orange brown, or orange red, or whatever you want to call it, gaseous material in there, and that represents a chemical equilibrium that's taking place. It's an equilibrium between N2O4 gas and NO2 gas. So it's very simple. The N2O4 decomposes to form 2 NO2 molecules, and that's the forward reaction is the way it's written. But at the same time, the two molecules of NO2 are reversing themselves and forming the initial reactant of N2O4. This substance under these conditions establishes an equilibrium between the two, and we can see that there's a relatively large amount of the NO2, because the NO2 has that color. The N2O4 doesn't have a color, but the NO2 has a color, and we can see that there's a relatively good amount of NO2 in there. And so the forward process and the reverse process are happening at the same time and at the same rate, and that the two substances, their concentration does not change. It remains the same. Constancy through change. So, looking at about 3 different scenarios, well, it's not about 3, it's definitely 3 different scenarios. We can see one scenario in which we start out with nothing but NO2. So if you look at this scenario right here, we start out with NO2. And of course, as time goes by, the concentration of NO2 drops, because of course it's becoming N2O4. Then we can begin to see the concentration of N2O4 begins to rise at the same time that the concentration of the NO2 drops. As the concentration of the NO2 drops, as we saw, the concentration of the N2O4 increases. So as time goes by, the NO2 concentration drops, and then it begins to level off. And we see that the concentration of the N2O4, it rises, and it begins to also level off. Of course, the reaction starts going in the first direction only at first, because there's all NO2 and no N2O4. And very little of it is actually going in reverse. And so we can see we get to a certain point where things start to level out, and the reactions reach a point in which we have the concentration of N2O4 and the concentration of NO2 stabilizing. So what does that mean if those two concentrations stabilize? It means that's the point at which we reached an equilibrium. The concentration of NO2 and the concentration of N2O4 are now equal, not equal to each other, but constant. Excuse me. You can see that they're not equal to each other. They're constant. At first, the NO2 concentration was dropping and the N2O4 concentration was increasing. The NO2 reaction, the reverse reaction, was taking place more readily. And until we start building up some N2O4, then and only then will it begin to go backwards. And as the amount of N2O4 builds and builds and builds, the forward reaction starts taking place more and more and more until finally we reach the two reactions happening at the same time and at the same rate. And since they're both concentrations have stabilized, we have equilibrium. And of course, there it is. Looking at the next scenario, let's start with nothing but N2O4, which is our reactant on the left in this case. And of course, we see that its concentration is dropping at first, and the concentration of NO2 is increasing. And of course, the forward reaction is going to take place mostly in the beginning because it's all N2O4. And as the amount of NO2 starts to build up, the reverse reaction starts happening more and more and more, until finally we see that the two concentrations have become constant. Not equal, but constant. Remember, one thing we should remember is that the concentrations don't necessarily have to be equal to each other. They may be, but in most cases they're probably not. But they have stabilized, they're not changing, and therefore we have to be in an equilibrium at this point. And then last but not least, in the third scenario, we can start with both of the two materials, and we can see the concentration of the N2O4 increases in this case, the concentration of the NO2 decreases in this case, and we establish an equilibrium at the point where the two concentrations become stable. They stop changing. And so it really doesn't matter in terms of equilibrium whether we start with all NO2 or all N2O4 or a combination of both. If we start out with the correct conditions necessary to establish that equilibrium, we will establish that equilibrium regardless of what we start with. Now, for a particular NO2 to N2O4 system at 25 degrees Celsius, here are a measure of the initial concentrations of NO2 and the initial concentration of N2O4 for various experiments. So you can see in the beginning we start out with nothing but N2O4, and in the last experiment we start out with nothing but NO2 because this concentration is 0 here and this concentration is 0 here. So we start out with nothing but N2O4 in the first experiment, we start out with nothing but NO2 in the second experiment, and the concentration is varied through, based upon what the experiment is. And then the equilibrium concentrations are measured for each of these substances at, during those particular processes. And then what was done was the concentration of NO2, which was on the right-hand side of the equation, over the concentration of the N2O4, which was on the left-hand side of the equation. That relationship was established, and the concentration of NO2 for each experiment was divided by the concentration of N2O4 for each experiment, and we can see that the 0.0547 divided by the 0.643 is this value, and the 0.0457 divided by the 0.448 is this value, and so on. And we can see it really doesn't tell us much. In this case, though, we took the NO2 and raised it to the power of its coefficient. And when we did that, and remember these are the equilibrium concentrations, and now this concentration is raised to the power of its coefficient, and this is raised to the power of its coefficient, we see something interesting happens. Within experimental error, because again these are experimental data, we get the same value for the most part. So something interesting is happening. Apparently, if we take the concentrations of the products, the stuff on the right-hand side, at equilibrium, and raise it to its coefficient, and divide it by the concentration of the reactants, the stuff on the left-hand side of the equation, raised to its coefficients, we get a constant. So for this reaction, the constant, which we're going to give it the symbol capital K, or in this case K sub C, because it's a concentration constant, is equal to the concentration of the NO2 squared at equilibrium divided by the concentration of N2O4 at equilibrium. And it comes out to 4.63 times 10 to the negative third. And it has no units. So the value of K, the constant, is no units. For a reaction A with a coefficient of A plus B with a coefficient of B in equilibrium with C with a coefficient of C and D with a coefficient of D, K is equal to the concentration of C raised to the C power times the concentration of D raised to the D power over the concentration of A raised to the A power times the concentration of B raised to the B power. And again, these are all equilibrium concentrations. So if you take the products and put them up top, raised to their coefficients, the concentrations of, and we take the concentrations of the reactants raised to their coefficients, what we normally call the reactants and the products, we get the value K. This is known as the law of mass action. The law of mass action says that this relationship is always true. So regardless of how much C, D, A, and B we start with, this should always be true. This reaction, no matter how much of these four things that we start with, is going to move in such a way so that the concentration of C raised to the C times the concentration of D raised to the D over the concentration of A raised to the A times the concentration of B raised to the B is always equal to the constant K. So this is true for this reaction. When K is much, much, much greater than 1, that means the equilibrium will lie to the right and will favor the products. So when K is a large number, that means the concentration of these two, which we call the products, is much greater than the concentration of the reactants. And so the reaction, although it's still going in both ways, it's still in equilibrium, the concentrations of these two will be much greater than these concentrations, and we say that it lies to the right or favors the products, which is maybe something that is good. And so small amount of reactants, large amount of products when K is greater, much, much greater than 1. When K is much, much less than 1, we say that it lies to the left and that it favors the reactants, so that the amount of reactants is much, much greater than the amount of products, which seems to make sense because these two values, this product is going to be small, this product is going to be large, so K comes out to be less than 1. And when these are big, it means that it lies to the left, it lies to the favors the reactants. So we'll still have an equilibrium, and there'll still be some C and there'll still be some D, but there should be much more of A and B. Homogeneous equilibrium. That applies to reactions in which all the reacting species are in the same phase. For example, both of the substances in this process are gases. So the K sub C is equal to the concentration of NO2 squared over the concentration of N2O4. We can also establish what is known as a K sub P. This is based upon pressure. Now we're not going to go through the derivation, and if you'd like to go through the derivation, you can certainly look it up in your textbook. But the K sub P is going to be equal to the pressure of the NO2 squared over the pressure of the N2O4. So in other words, if we take the pressure of the NO2 raised to the coefficient in the equation over the pressure of the N2O4 raised to its coefficient in the equation, we get this constant known as the K sub P. So basically we're replacing concentration with pressure, and it's just the pressures of the products raised to their coefficients at equilibrium, of course, over the pressures of the reactants at equilibrium raised to their coefficients. And again, we have to be careful because these are concentrations, and concentrations could be established for more than one thing other than gases. But these, of course, are pressures, and pressures are only established for gases. So because this is true, because that this is a constant dealing with only gaseous substances in the reaction, and this is a constant that deals with more than gaseous substances in the reaction, K sub C does not necessarily equal K sub P. But there is a relationship between K sub P and K sub C. We're not going to derive it here in this video, but if you would like to see it, you can go in your textbook and take a look. And for a reaction in which A raised to the A power, that is gaseous, plus B, I'm sorry, not A raised to the A power, A with a coefficient of A plus B with a coefficient of B in equilibrium with C with a coefficient of C and D with a coefficient of D, all three substances, of course, all four substances, of course, being gaseous. In this case, K sub P is equal to K sub C times R times T raised to the delta N power. And again, they don't all have to be gaseous substances, right? That's why we said there's a difference between K sub C and K sub P. Not all reactions contain 4 different gases, okay? It might contain 2 different gases, or it might contain 2 gases and 2 aqueous substances, or it might contain a solid or liquid and some gaseous substances. But not everything in the reaction is going to be gaseous. And so, my friends, be very careful, because delta N is equal to the moles of gaseous product minus the moles of gaseous reactants. Be very careful. You don't know how many times I see students solving this problem, and they would put in the number of moles of gaseous product and the number of moles of other products that are not gaseous and moles of gaseous reactants, but again, moles of other substances, other reactants that are not gaseous. So they ignore this idea and they put however many moles on the left and for moles of gaseous reactants, and however many moles, total number of moles, on the right for the gaseous products. That's a mistake. So in this case, since they're all gases, it's the coefficient C plus D minus the coefficients of A plus B. If they're not gases, if A was not a gas, then it wouldn't be in there. If D were not a gas, it wouldn't be in there. And of course, T is in Kelvin, and R is the ideal gas law constant, and that's 0.0821 liter atmospheres per mole Kelvin. Homogeneous equilibrium. Homogeneous equilibrium is equilibrium in which we have all the substances in the same phase. K sub C with a prime next to it is equal to the concentration of CH3COO minus raised to its power, which is the first power, because the coefficient is 1, times the H3O plus concentration raised to its power over the CH3COOH concentration times the H2O concentration, of all of which are raised to their powers. Now, the concentration of water is thought to be a constant. The concentration of water in this case, because it's a liquid, is going to be very high, and it's basically not going to change. So for all intents and purposes, the concentration of liquid substances in reactions basically don't change. If this reaction takes place in a liter of water, 1 liter of water is basically 55 moles of water. 55 moles of water per liter. That's a large concentration. All of these others will be very small compared to the concentration of the water. So for all intents and purposes, the concentration of the water doesn't change. It remains constant. And so the K sub C for the final reaction, the final K sub C, is equal to K sub C prime times the concentration of water. And so the K sub C is equal to the CH3CO minus concentration times the H3O plus concentration divided by the CH3COOH concentration. We do not put liquids into the K sub C expression. The only substances that we put in the K sub C expression are gaseous substances, which we don't have any in this equation, and aqueous substances. So stuff dissolved in water and gases are involved in the law of mass action, the K sub C expression, where you take the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients to get the value of the K sub C. And remember, it doesn't matter what these concentrations are when you first start. They will always change in such a way so that this ratio is always going to be equal to the constant. And that constant will be established for that particular reaction, which you can find in your textbook. And remember, we said that because the H2O concentration is constant, the K sub C prime times the concentration of the water is equal to the final K sub C, where the final K sub C is equal to the concentration of the aqueous products raised to their coefficients at equilibrium divided by the concentration of the aqueous reactants raised to their coefficient at equilibrium. General practice, do not include units for the equilibrium constant, as we said earlier. So here's a problem. The equilibrium concentrations for the reaction between carbon monoxide and molecular chlorine to form COCl2 at 74 degrees Celsius are: the carbon monoxide concentration is 0.012 m, the Cl2 concentration is 0.054 m, and the COCl2 concentration is 0.14 m. Let's calculate the constants K sub C and K sub P. Well, here's the reaction, and it's already balanced, and we can see that we've got a double arrow in there, so we've established it as an equilibrium. The K sub C is going to be equal to the COCl2 concentration at equilibrium raised to its coefficient divided by the CO concentration raised to its coefficient times the Cl2 concentration raised to its coefficient. And again, all of these concentrations are the equilibrium concentrations. So we plug in the values that are given, and they're all concentrations in moles per liter. We turn the crank, and we get 220. Now that's a pretty big K. So that, since it's a pretty big K, it tells us that it lies to the right. When you take right and lies and put them together, you get rise. So it lies to the right, because that's a big K. It's much, much greater than 1. And so since it's much, much greater than 1, it lies to the right, and we're going to have more product than we are going to have reactants. In order to find the K sub P, remember we said K sub P is equal to K sub C times R times T to raise to the delta N power. So K sub P, well, delta N is 1 minus 2, because there is 1 mole of gaseous substance here and 2 moles of gaseous substance here. We go based upon the reaction. We go based upon the equation. The value of delta N is determined in this case in terms of the stoichiometric relationship. We don't need to do it based upon these concentrations. We don't have any values, we don't have any information here in order to even try to find out what the actual number of moles are. And the delta N would come out the same anyway. So we've got 1 mole of this in the equation, we've got 2 moles of these in the equation, and 1 minus 2 obviously is negative 1. The value of R is 0.0821, and that's in liter atmospheres per mole Kelvin. And of course T is in Kelvin, not Celsius, so we add 273 to 74 and we get 347. And we plug in the numbers and we get a value of 7.7, which again is much, much greater than 1. We can consider that to be greater than 1, and of course that's what it's telling us, just based upon pressure, is that the pressure of the COCl2 is going to be much greater than the pressure of these two. And if that's the case, if the pressure of the COCl2 is much greater than those two, then obviously there is much more COCl2 than the other two. Now let's try another problem. The equilibrium constant K sub P for this reaction is 158,000 Kelvin. What's the equilibrium pressure of the O2 if the pressure of the NO2 is 0.400 and the pressure of the NO is 0.270? So the K sub P, which is what we're looking for, or not, sorry, it's not what we're looking for. We're looking for we're looking for the pressure of the O2. But the K sub P is equal to the NO pressure squared, right, raised to its coefficient, times the concentration of P raised to its coefficient, divided by the, not the concentration, let's try it again, the pressure of P divided by the pressure of the NO2 raised to its coefficient. And we can rearrange the equation to solve for the pressure of the O2. And of course, we have the K sub P, we have the pressure of the NO2, we have the pressure of the NO. We can just plug all those values in. And of course, since they're raised to their coefficients, we have to square them. And the pressure comes out to be 347 atmospheres, which you can see is much larger than 0.4 atmospheres and much larger than 0.270 atmospheres. So we can see really big K, right? Much, much greater than 1, means reaction lies to the right, and that can be seen by the fact that the pressure of the oxygen is 347 atmospheres. 347 atmospheres, much more oxygen than anything else. Heterogeneous equilibrium applies to reactions in which reactants and products are in different phases. Like this reaction right here. We have a solid calcium carbonate decomposing the solid calcium oxide and carbon dioxide gas. See, solid gas. So the case of C, well, that's going to be equal to, based upon what we've talked about before, CaO solid times CO2 gas over CaCO3. But the concentration of those two solids, like liquids, don't really change much. Okay? In fact, they change basically not at all. And so we consider those to be constant. And of course, we don't worry about them when it comes to the case of C. The case of C just ends up being equal to the concentration of the CO2. So the case of C is only dependent upon gaseous species and aqueous species, as we have seen. Remember, the case of C, which is equal to the concentration of the CO2, is just the case of C prime, written as it is for this expression here, times the ratio of those two because they're constants. And so the case of C is just equal to the CO2 concentration in equilibrium. And of course the case of P is only dependent upon the one species that has a pressure, and that is the pressure of the CO2. If the CO2 were on the other side of the equation, then the case of P would be equal to 1 divided by the pressure of the CO2. The concentrations in solids and pure liquids are not included in the expression for the equilibrium constant because they themselves are constant concentrations. We only put those things in the expression of the equilibrium constant which have the opportunity to change their concentration as we go from initial concentrations to equilibrium concentrations. And therefore, we do not, repeat, do not put solids and pure liquids in there. Okay. The pressure of CO2 equals to the case of P in this case. So, we have a situation in which we have this reaction occurring. We have this amount of CaCO3 and this amount of CaO, and we've got the CO2 in the air. And we've got this amount of CaCO3 and this amount of CaO, and we see that the quantities of those two are different in the two experiments, but yet the pressure of the carbon dioxide we can see as we go from this height to this height for this experiment and this height to this height for this experiment. It doesn't matter how much CaCO3 or how much CaO you have, the pressure of the CO2 is always going to be the same because it's equal to the case of P. See, the pressure of the CO2 does not depend upon the amount of CaCO3 or CaO, which I just said. Okay, consider the following equilibrium at 295 Kelvin. NH4HS in equilibrium with NH3 plus H2S gas. And we have two gases in a solid. The partial pressure of each gas is 0.265 atmospheres. Let's find the case of P and the case of C. So, the case of P is going to be equal to the pressure of the NH3 times the pressure of the H2S, both of which are raised to the coefficient of 1, divided by, no gases on this side, so nothing. We put in the partial pressures and we calculate the K sub P, which kind of tells us that there really isn't a lot of these two over here, and actually this solid doesn't really decompose all that much. Now let's find the K sub C. Remember, the K sub P is equal to the K sub C times R times T raised to the delta N power. We rearrange the equation in terms of K sub C. We plug in the fact that delta N is equal to 2 moles of gas on this side minus 0 moles of gas on this side, which is 2. And T is equal to 295 Kelvin. We plug in the number, and of course this is raised to the negative delta N power, and it comes to 1.20 times 10 to the negative 4th, which again tells us this is a value that's much less than 1, so it tells us that there's not a lot of these two, and mostly this solid is left in the container. Okay, well that ends this video, and we'll move on later on to another video later. So have a good night.